So we'll do that from here on out because I have a feeling it's going to be easier to see the board. So change of base. Change of base. And yes, this does, I think, I heard that this came up on some of the math or the academic team. So the change of base is kind of nice. It's actually very nice. Because it says that log base a of x is equal to, well, they'll call log base b of x over log base b of a. Or really, we can say that log base a of x is equal to log of x over log of a. And the reason I just say log is because we're changing the base from base a, and this really needs to be lowercase if we're going to be accurate, to base 10. We're wanting to change it to base 10. Now, what's really interesting is this is actually the same as ln of x over ln of a. It actually works out to be the same thing. Log base a of x is equal to ln of x over ln of a. It actually works out to be the same because we're really changing it to base 10. Or some other base, we could do it that way. It's not, we don't normally do this here. That's not something we would normally do because if I'm changing the base to something else, I really don't want to change it to some other number. Does this make sense? Because the only reason I would change the base to something different is if something's simplified. Because if the base and the number inside the parentheses simplify out, then they have that in common, yes? That'd be the only reason to change it. But if it did, like up at the top, it had a common, it was 2, base and number were 2, well, I could have simplified it to begin with. There's no reason to change the base. Y'all get where it's going there? Because if we had something like log of base 2 of 2, there's no reason to rewrite this as log of 2 over log of 2, because log base 2 of 2, that simplifies. Does that make sense? Because that log base 2 of 2 is 1, because when the base and the number inside the log are the same, it simplifies to 1. That's one of our properties. So there's no reason to simplify that. If I'm trying to simplify, it'd be log base 7 of 3. Well, I can't do that in a calculator. Well, we can with the graphing ones, but a standard graph or calculator doesn't do that. I'd have to change it to log of 3 over, and then I can figure this out. Or this is actually the same as ln of 3 over ln of 7. Questions on this here? One way to look at the change of base formula is that the logarithms with base A are simply constant multiples of the logarithm with base B. The constant multiple is given in that form there. But let's look at this here. So how would I write this as the change of base? 5 over of log of 4. Or as a natural log, we would say ln of 25 over ln of 4. That there's my way I've gotten, that's just another way, a lazy man's way of writing ln. They just merged. I'm showing you that there because if I may or may not, I normally don't, but if I happen to throw that up there, that's ln. And talking about it, sign. When you talk about the limit, I picked that up from my college professor, the way he wrote them. But that's it. That's all we have to do for these here. I only did one of them because I feel like the change of base is, we're good with this here. We're good with change of base. Now, there are some properties of logarithms, and they're kind of talking about these inverse here and whatnot. But these here, they work with log properties, the product property, the quotient property, and the power property. These all work with logarithms. So if we have the log of any two things multiplied together inside the log, it's the same as adding them together. Log of m times n is the same as log of m times log of n. Quotient property. When we have two things being divided inside the log, it's the same as log of u minus log of b, yes? And power property, log of, I'll say m to the n, is equal to n log of m, yes? So we're good with this here so far. And the same thing is true with natural logs. So we'll say this is true. I can get the other ones using this property. That seems a little weird, yes? So we can get division and powers from this here? Well, let's say I had log of m divided by n, yes? Would this be the same as log of m? Actually, let's do powers first. I'm going to do powers first. Log of m to the n, yes? Well, this is the same as log of m times m times m going on out, yes? Because a power is just saying it's that number times itself so many times, n times, yes? So we have m multiplied by itself over and over and over again, yes? Well, it's the same as saying log of m plus log of m plus going on out, yes? Because our first property, our product property with logarithms inside the logarithm is that any two things or any multiple things multiplied together inside the log, we can rewrite it as addition of those logs, yes? Well, doing this here, we have n multiplied by itself how many times? So how many sets of additions of m would we have? N. So we really can say this is n times log of n because we have n number of them, yes? Didn't we just prove the power rule? That we can move the power out front? Okay. So the power rule really comes from our product rule, yes? So we've proven those two to be true. We've also proven that log of m to the n is equal to n log of m. And I needed both of these. Because now if we look at, say, log of m over n, is that the same as saying log of m times n to the negative 1? Because we can move it up from the denominator to the numerator, and we make the exponent negative. Okay, first property, well, this says that I have log of m plus log of n to the negative 1, yes? Well, we just proved with our power rule that I can move that exponent out front, yes? Well, that changes it to what? Log of m minus log of, we just proved our division rule. Does this make sense here? So the product, it's really, these here are just using, we can prove them from one to the other. We won't ever have to do that. You won't have to do that again. We just have to remember that if we have a division inside the logarithm, we can rewrite it as subtraction. If we have a multiplication inside the log, we can rewrite it as addition. And powers of powers will simplify. Or we can move our power product property. The exponent comes out front. Now, this seems kind of odd. Why would we do this? The reason we would do a lot of these here is if we're trying to simplify. Now, ln isn't going to be too helpful, but this here is working on us being able to do that because we want to rewrite this in terms of 2 and 3, ln of 2 and ln of 3. So when we get done, we'll have that. Now, what is 6? 6 is the same as 2 times 3, yes? Multiplication property would say that this is ln of that's it. That's all we have to do here. So this is just working on those properties. Ln of 2 over 27. Well, that's division, isn't it? So I can rewrite this as ln of 2 minus ln of 27. Well, the first one, ln of 2 is fine, because we do have that in terms of ln of 2, yes? But I don't have ln of 27. I can't leave it as that. But what is 3 to the third is 27, yes? We can move it out front and get ln of 2 minus 3 ln of 3. Now, what you were saying, yes, that would work. Because what we could have done is gone from this here and said that this is 3 times 3 times 3, or 9 times 3, and broken it up that way, which would have been ln of 2 minus ln of 3 plus ln of 3 plus ln of 3. We've got to put parentheses around it. We have to put parentheses around it. Because if we're not paying attention, each one of these here is actually negative. Yes? Because we're subtracting it, our property of our multiplication property, our product property with logarithms, says that we add them together. But because of that negative out front, all of them would have to be negative. And we could combine them and get negative 3 ln of 3. Well, ln of 2. Now, we could have skipped that entirely and said ln of 2 minus, combine them before we drop the parentheses, and got into this here. I don't know about y'all, but I think this way is a little bit easier, isn't it? Yeah. So again, this is one of the, well, side note, tangent. If you've ever wondered why I use parentheses like crazy most of the time, because you probably thought that in geometry and algebra too, why are we using these parentheses for absolutely no reason? Because a lot of the times the parentheses just dropped away, yes? It really didn't change anything. Here's one of the reasons. Because of that negative. Since I applied that property, if I didn't have those parentheses, there's a good chance I would have left these two here as positive and only affected the one, which changes everything. Does that make sense? So having parentheses, and sometimes I will use brackets. Parentheses and brackets are interchangeable when you're writing it. So if you start getting a lot of parentheses put in there because you're putting multiple things in, I will sometimes switch and alternate between parentheses and brackets to make sure I've got enough to see what is connected. Does that make sense? And most likely you're never going to come across something like that where you need a whole lot of those. But that's what we just did. Questions on this here? Any questions on anything we've done so far? Rewriting logarithm and exponential. So what we're going to do is we're going to start out with something like this here, and we want to simplify it all the way down as possible. Simplify it as far as possible. So when we get done, we don't want any logarithms that have multiplication powers or division inside of them. The first one I would always do first when expanding, division. I would always do division first. because division deals with a negative. Negatives are tricky because we got to make sure the signs are the same. Kind of like the last one where we had the LNs broken down. The negatives can change what it is. Yes? So I would normally do division first. Well, there's not any division here, is there? No. So multiplication would tell me that this is log base 4 of 5 plus log base 4 of plus log base 4 of yes. Well, those two are done because there's nothing else we can do with it. But the middle one does have an exponent, yes? So we would move it out front. That's it. Questions on this here? We feel good with this here? So again, when I look at this here, the first thing I would do would be the division. I would deal with it first. So that would rewrite this as ln of the square root of 3x minus 5 minus ln of 7. Well, the ln of 7 is done. There's nothing else down with 7, is there? Technically, this is not the last step. How would I rewrite a square root as a power? Because again, radicals can be rewritten as fractional exponent or rational exponents. And as a side note, the nth root of a to the x is the same thing as a to the x over n. And whenever there is not a number written inside of the radical, an index for the radical, it is always understood to be what? 2. It's always understood to be 2. So the square root would be 1/2. Questions on this here? This is very helpful or handy to have because if you're having difficulty or don't have a calculator that can do square roots easily, because a lot of the online programs, if you haven't figured it out yet, they don't do square roots well. Like Desmos graphing calculator, I haven't looked into it too hard. It probably does. But if you're really not wanting to dig in there and find the square root, it's pretty easy to do a fractional exponent, yes? Because I can do an exponent 0.5 or 1/2, and I'm done. I don't have to find it. Does that kind of make sense? So if I don't want to go searching for it, I'll just do 1/2. But we can move it out front, which tells me that this is 1/2 ln of that's it. Questions on these here? Questions on any of these here? We good with these here? We want it simplified. We wanted to expand it all the way out because the square root is same as having a fractional exponent. We can move that out front. So that way, if we're trying to solve this here, I'm not having to take the natural log of a square root. I'm just taking the natural log of that. And it's a little bit easier to solve. Any questions on this here? We can go the other direction. We can go the other direction. Now, we only did a few of these, but what was the last thing we did when expanding was powers, our power property? That's what I do first. When I'm trying to put it back as 1, I do power property first. ln of x. Now, how do we want to move the 4? Do we want to move the 4 up or the negative 4? We can do negative 4. There's nothing wrong with that, because that would give me ln of y to the negative 4, yes? What would the sign be? Positive. Since I pulled the negative out, it's going to be positive. And we can do the same thing with the negative 3. Any questions on this here so far? Now, they're all added together, yes? So that means I could rewrite it as multiplication, yes? We have ln of 7 to the 3rd times x times y to the negative 4 times x to the negative 3rd. Well, as you've discovered having math is for so long, I can never leave exponents negative. That's one of the things when we talked about exponents in Algebra 2. We cannot leave them as a negative. But I can move them from the numerator to the denominator. So 7 cubed would stay, x would stay. X to the negative 3 would be in the denominator, and we would have y to the 4th, yes? I can't leave this as this. I can't leave as everything as it is. Can I do 7 to the 3rd? Can we simplify that to a number? Yeah, what is 7 to the 3rd? 49 times 7. 9 times 7 is 63. 3 carry the 6. 28. 343. I'd go on and double check my math. Sweet. Now, would we have the x also in the numerator? No. Because since I have an x on top and bottom, you can simplify one out. Now, we could have simplified it here, because when the bases are the same, we add the exponents. When we're multiplying like bases, we add the exponents. 1 plus negative 3 would have given me negative 2, which would have moved down. Questions on this here? We good with this here? Now, doing this here, really in this first step, pulling those exponents, a negative with that exponent, with the 4 and the 3, made this easier. Made this easier to work. Because what we would have had to do instead of that is factor that negative out, then write it as division, and then go on from there. So pulling that negative with it actually made this easier. I think it made it easier. Any questions on this here? We good with this here? Application. So one method of determining the x and y values for a set of nonlinear data are related is taken to the natural logarithms for each value of x and y at the point x. If the points when graph fall in a line, then you can determine that the x and y values are related by the equation this, where m is the slope of the line. So the mean difference. So the tables show the mean difference from the sun and the period y, the time it takes to a planet to orbit the sun for each of the 6 planets that are closest to the sun. In the table, the mean distance is given in terms of astronomical units, where Earth's mean difference is defined as 1, and the period is given in years for each equation that relates x and y. So really this is determining it based off us. So it's all based off planet Earth. So if 1 is Earth, well, Venus is going to be 0.287 is faster. If it's above 1, it's slower than Earth. It takes longer. That's really all it's talking about. And we can see the mean difference, so it will be kind of an exponential function as we get farther and farther away from planet Earth. And we can talk about the slope, and that this here would give us an equation that would be the approximate period or time it takes to revolve around the sun the farther we get away from Earth.